go to the next one. Dr. Shammi Kaya. Yeah, thank you.
Hello, everyone. Today I'm going to talk about built environment and urban climate, urban microclimate, and the topic is about integrating urban built environment and microclimatic effect analysis for energy planning in cities. I'm pursuing my doctoral studies in the University of Eastern Finland, and I'm currently working in the project called Sustainable Building Technologies. The project, if you want to know more about this project, you can scan this QR code, and these are the partner universities involved in this. The research activities supported by this project includes the spatial modeling for climate-wise construction and urban morphology and energy consumption nexus-based framework, materiality and urban microclimate, impact of building envelope material on urban microclimate, investigation of long-term indoor air quality in wooden wall structures, and finally, the development of the sustainability index from the summary of all the earlier results. So the study starts with acknowledging few of the factors that we can see here. First is the construction sector is not on track to decarbonize by 2050. 73.2% of the global greenhouse gas emissions is caused due to energy uses. Building sector centrally holds 17.5% of the share. Buildings are responsible also for 50% of extracted materials and 33% of waste and water uses. The recent agreement of the European Commission establishes an EU energy efficiency target of 11.7% for 2030. And to achieve this, there has been some steps, proposed steps, which includes promoting local heating and cooling plants in large municipalities having populations above 45,000, revised definition of efficient district heating and cooling, EU countries' obligation to renovate each year at least 3% of the total floor area of buildings owned by the public administration and also covers the regional and local levels, which opens the possibility of adjusting the architectural design of buildings to better perform in different climatic conditions. Now the question stands how to develop a systematic and quantitative decision support system to optimize energy and material uses in building and city scale. The methods, here we can see how the qualitative data and quantitative data has been used in this study. First, we have conducted the literature review to have a better understanding of the indicators that affect the microclimate in cities. Then the quantitative data included the morphological analysis using building locational data. The building locational data was provided by the city of Joensuu, where I'm conducting this study from. Then the U-value and weather data from Open Data Platform, and also the spatial analysis in GIS, and the index was calculated using Excel. Here we can see how all the indicators have been compiled together to calculate the potential impact of within a city under different microclimatic conditions, and then how we could utilize the building scale parameters to assess the adaptive capacity of a building to have a better understanding how the building will perform under a certain extreme weather condition, and then further going towards to vulnerability assessment, and then towards proposing interventions in the specific context. To give us a small overview of the city that I have been working on, here you can see the map of Finland, and the city is called Joensuu. It's actually 500 kilometers up northeast from Helsinki. The population is 77,480 people, and it's also considered or mentioned as the forest capital of Europe because the European Forest Institute is based in this city. Now, a little bit overview of the climate data for the selected case study city. Here we can see that under extreme conditions during summertime, the temperature can go up to 37 degrees, and then during winter time it can go up to minus 39, which explains the continental climatic conditions of the city also. And in the bottom chart within this slide, we can see that how the temperature anomaly of the city has gone up, and it's showing the increase in the overall temperature during the recent years. And here we can see the past 3 years climatic temperature data here, and how the summertime has been moving from starting from May, and then during the last 2 years it has been moving from June and July. So the city is facing a slightly longer summertime and a bit milder wintertime. So why is it necessary to consider all these parameters that I've showed before? Here we can see that the different external parameters, which is basically causing the buildings within the city to be exposed to the extreme temperatures in summer and winter time. First, we have started with analyzing the land surface temperature, solar radiation, air speed, air temperature and wind speed, and also the occupants number in all the buildings. And then for analyzing the internal urban morphological qualities, which is explained as the sensitivity, we can see that the mass volume to heat and or cool was considered, and also the porosity, which explains how densely the city is built, and then also the proximity to water and green. And then finally, the adaptive capacity of the selected context. Here, to assess the adaptive capacity, the building-based data, which is the U value, and then the normalized constructed carbon sink volume within the 250 meter buffer from the building locations, and then finally the normalized vegetation index was considered. And then all of these parameters, indicators was used to calculate the extreme weather vulnerability of the city. Here we can see how the wintertime potential impact is showing in the city, and then the summertime potential impact, and then finally the total potential impact. The key factor here to notice is that this index is considering both of the time, both of the extremities, summertime and winter time, within a selected context. And the variable here is that the count of cold days divided by the total days within a year, and then another variable is the count of hot days, total hot days, and then divided by the total days of the year. Then we can see what is the inclination towards heating load compared to the cooling load. And in this map, we can see that once we have the localized score within the city, even within a selected score of potential impact, how the building is going to perform, that is going to give us the final score of the building's vulnerability in the final stage. So we have, for example, here one area with the potential impact of 0.36, and then we have added the building's own resistance or the building's own performance indicator here explained as the U value, and then we have the final building specific vulnerability explained in the end. So using these parameters and using this index, what we can do is we can divide interventions in two scales. First is building level intervention, which is the evaluating improvement, utilizing carbon storage and reused materials in buildings, solar panel installation, facade greening, user-oriented instruction. By user-oriented instruction, I'm referring to, even though a building is very well designed and located in a very good context under very good climatic conditions, if the users are not aware enough, they will still use a lot of energy, and regardless whatever benefits you're giving them. And then under the neighborhood level intervention, which is going beyond the building's capacity, there we need to intervene in the neighborhood scale. And then we can increase the neighborhood level greening, solar panel grids for heating, low carbon infrastructure, and reduce road density. Therefore, coming up with a more structured way of looking at the city to promote this the heating and cooling plan within the city, considering its own built environment and own microclimate. Thank you. For further information, please scan this.